Welcome back from that break. I hope you're doing well. Let's get into a little bit more about the electrolytic cell. So our focus today is on the electrolytic cell, and in this section I want us to take a look at the link between the electrolytic cell and the standard reduction potentials. So you will remember the standard reduction potential table. It's that table with all of the half reactions, they're reversible reactions. We're going to link those to the electrolytic cell. We did it with the galvanic cell. Now we're going to look at it and the electrolytic cell and see what we can do with that table and the electrolytic cell. Here's what we're going to be able to do with it. So when we have the table of the half reaction table, the first thing we can certainly get practice is to write down the net reaction of an electrolytic cell. We're going to do some examples of that. We're also going to determine which ions in the electrolyte. So they're in the electrolyte. If we have more than one different type of ion, they will react differently. We'll have to decide which one's going to react and which one's not going to react. So it's very important. We can use the table to help do some reasoning about what's going to happen there. And then the final point is that we're going to be able to calculate the EMF or the E naught. This is also equivalent to the EMF of the electrolytic cell. Remind you, the equation, which is on the data sheet, is E cell is equal to E naught of the cathode minus E naught of the anode. The equation is exactly the same as we used for the galvanic cell. So there's no new learning. It's all about just applying it to a new situation. Let's go and see that writing down of the net equation. So we're going back to our electrolysis of copper chloride. Here's the word equation. Copper chloride goes to copper plus chlorine. You can see the chlorine gas there. You can see the copper deposited over there. So this is even the half reaction that we've got. Copper ions plus chloride ions are going to give us copper and chlorine. We got that just by looking at the half reactions, the equation of the oxidation equation, the reduction equation. We put them together and that's the net equation. But I want to go through looking at it in a little bit more detail, extracting the information from the table. So the first thing we need to know, and we need to identify this clearly, is the things that are on the left-hand side of this equation are known as the reactants. Those are the things that we've got at the start before the switch was open. So what did we have at the beginning? We've just got the ions that are in the electrolyte. We're then going to turn on the switch and there's a chemical reaction that takes place. The redox reaction takes place and then we're going to get the products. So let's go to our table now. All of these reactions on the table, there are many of them. We're going to have to look for the reactants. We're going to have to look for the products. If you remember when we did the galvanic cell, we started on the right-hand side of the table and we ran our finger down until we could find the strongest reducing agent. So let's do exactly the same here. So remember, lithium at the top of the table, the strongest reducing agent, most reactive reducing agent on this list, and we run our finger down. Now what are we looking for? We're looking for something that we started with. We're looking for copper ions or chloride ions. And as I'm looking, I'm not seeing anything. Right down at the bottom over there, I see copper. Now, was copper a reactant or was it a product? No, it was a product. So we can't use that one. It's not the reactant. You will notice that if you cast your finger to this side of the table, there are the copper ions. So they're on the wrong side of the table. We can't choose them. So let's go lower down in the table and see if we can find either the copper ion, so that's the copper metal, there's the copper ion. We're not interested in that at the moment. We're interested in finding if there's a copper ion here. So I look down, don't see a copper ion. There's an ion. There's a bromide ion. There's no copper ion, but wait, there we go. We found the chloride ion. That's what we want. It's the strongest reducing agent of those two reactants that we start with. But now where are we going to look for the other component? This is the reducing agent. Where is the oxidizing agent? Normally, for the galvanic cell, we would have gone across over here and we would have started to look down there. Now, none of those are copper ions. So what we're going to have to do is say, here's something different. When we have an electrolytic cell, it doesn't go down below, but it goes above. So we recognize that that's kind of a different order. It's going in that direction. So we pick up the reactants. We have to start with the reactants. Don't get the reactants and the products confused. And so we've identified the reactant as the chloride ion and as the copper ion over there, and we can then write down the equations. So you can see there's the copper ion, there's the chloride ion, and we've just extracted the equations off the data sheet. But now we're going to have to say which one is going to react. Well, clearly, what we're going to see is that the chloride ion will react to give us chlorine gas, and that is the oxidation reaction. Now remember, oxidation takes place at the anode. And that's important for us. And this reaction is going to be the other reaction, which is the gaining of electrons. So it's the reduction reaction. And that means that this has to take place at the cathode. And if we're going to write a net reaction, it means then we're going to have to write them in the right order. Writing in the right order so we've got to change the order of the copper reaction. We're going to rewrite it so that the copper reaction is fine. Sorry, the chloride reaction. We're going to say the chloride ion, this is the ion, the starting point. Notice the difference, chloride, and this is chlorine. So we're now writing it in the reverse order. We flipped it around from what it was before. Look, it was the other way around. We're writing what was on the right-hand side has now gone onto the left-hand side. And the chloride ion is going to chlorine gas, which is what we've observed. Now, in this case, we look at this reaction very carefully, and we see that look for the number of electrons. So the first thing to make sure is you've got the reactions written correctly from left to right, put them one on top of each other, and we're happy as they stand. We then check the number of electrons. 2 electrons were lost over there, 2 electrons were gained over there. So the balance of electrons is fine. We can cross those out. And to get to our next point is to write the net reaction, which means we've got to add these two together. So we'll start with the left-hand side, and we'll say 2Cl minus, aqueous, because ions have to be aqueous, plus Cu2 plus, aqueous, because those are below each other. Now we go into the other side of the reaction. This is the net reaction. Chlorine gas has been produced, and that's a gas, plus copper in the solid that's been plated to the electrode. And there's your net reaction, all nicely added together. No imbalance. Let's look at another example. In this case, we're going to do the electrolysis of acidified water. That's just water with a little bit of acid added to it, because pure water would not be a conductor of electricity. So let's see what happens in that reaction. Water will be broken down into hydrogen and oxygen. When we did this, we wrote the net reaction as 2H2O going to 2H2 plus O2. But how can we get that reaction, or a similar one, by looking at the half reactions? Well, you know what? Let's go and have a look at the table. And just like we started for the galvanic cells, we started on the right-hand side. And we're looking down here. The strongest reducing agents are on the right-hand side, and we're looking for water, or for one of the products. There's a product. We notice that goes with water on the left-hand side, so we'll keep that in mind as the first type of reaction that we've got. In fact, let's write that down as a half reaction. If we go further down, you will see we also get hydrogen there, but there's no water there. So we're going to choose that one because it's got water in it. And so I've got water plus 2 electrons to produce 2 hydrogens and 2 hydroxide ions. Now the hydroxide ions are important, but when we have a hydroxide ion plus a hydrogen ion, that will make water again. So we'll bear that in mind. In this case, we're now still on the look for water. Notice this is a hydroxide ion. It started with water and oxygen. We're not looking at that reaction. We'll cross that one out. It's not what we're looking for. There's peroxide, and there's oxygen there. It's one we can ignore. All the way down to here, there's water on its own. And we notice that we can write this with oxygen as a product and 4H plus 4 electrons. I'm going to write that down below my reaction. In this case, I recognize this is a gain of electrons to give me hydrogen. So that's the reduction reaction. This reaction is a loss of electrons, so it is oxidation. But now, because it's written on the table from right to left, I'm going to flip it around and I'm going to change it as I've done here, starting with water, producing oxygen, producing hydrogen ions, plus 4 electrons. Guys, I hope you can see that at this point, the electrons aren't balanced, so we need to balance the electrons to get a net reaction. So how are we going to do that? Well, we've got to count them, and we're then going to multiply through by a factor. So take a look. This one is 2 electrons, that's 4 electrons. To make that 2 electrons into 4, I'm going to multiply this whole row by 2. So everything in this row becomes twice what it is. So that's going to become 4. That's going to become 4 electrons. This is going to have a 2 here. This is going to be 4. Right. Now we're ready to cancel the electrons out, and we're ready to put lines through them so we can start to add them together. The electrons are now balanced. Let's add up just like we would for something in accounting. We're going to just make sure we add things together. 4 water plus 2 gives us 6 H2O. The electrons are cancelled, go to this point, 2 H2, which is what we had before, 2 hydrogen gas molecules, plus oxygen. Now, here's the combination that we're interested in. 4H plus 4OH minus. What do you think that's going to give us? Well, it's just going to give us extra water, which is like another bit of the product. So on this side, we can write down that we've got 4 water molecules. Because for every hydroxide, we're adding a hydrogen to get 4 water molecules. Add those together now, and look what happens. We've got an imbalance. We've got 4 on this side and 6 on that side. And if you remember in your maths, you can, what you do to the one side, you do to the other side. So I'm going to subtract the 4 from the left, from both sides, and I'm going to get 2H2O going to 2H2 gas plus O2, and I'm going to subtract 4 from both sides. And so that's how I end up with the same reaction using the standard reduction potential table. I hope you enjoyed that, and I hope you will practice some more of those, because it's a really important skill. Time for take a quick break, but we'll be straight back after that.